Hey guys, my name is Hiraku Murakami, back with NovaEdge Academics, and today we'll be continuing with topic A5 Relativity Part 3. So if you've missed the last two previous videos, they build up to this topic, so please, if you haven't watched them yet, then go check them out before you watch this video, okay? So we're finishing up this topic about space-time. In Newtonian physics, we measured space and time separately, and that was totally okay because they didn't affect each other, right? They weren't a function of each other. But when we considered special relativity and we did the Lorentz transformation where it included the effect of Lorentz factor and spontaneity, then we saw a little problem, which is that x prime was a function of x and t, or t prime was a function of x and t, right? So they're essentially telling us that x prime is a function of both position and time, and t prime is a function of both position and time as well. So they're just intertwining with each other and they're just mingling with each other. So we can't really measure them separately anymore. But here's one thing that we're going to see, which is that there's something called space-time intervals which are conserved. And I say conserved because this is how we basically find consistency between two different perspectives, two different reference points. For example, maybe I find the interval between two events from my side to be occurring 5 meters apart and 5 seconds apart. From your perspective, it might be occurring 10 meters apart in 3 second span. But there's something that I can quantify to basically match those two perspectives together and basically calculate that conservation effect. And I'll be explaining that a bit later and using space-time diagram to do so. Okay, so the following slides are going to be building up to how to do that. So the first is, before we think about space-time as the integrated component, let's think just space intervals. Okay, and you're going to see what those intervals mean because I'll take you step by step. So first we have 2D space, right? 2D space is just x and y. In x and y, we've always been doing this all the time, right? So as an example, if I have an event occurring at 0 and 0, and then so that's event A. And let's say I have a second event called event B here. So that's going to be at 3 and 1, 2, 3, 4, right? The interval between those two, or the distance between those two, is going to be following Pythagorean theorem, where I have 3 here and 4. So the hypotenuse is equal to square root of 3 squared plus 4 squared. Or h squared is always going to be equal to x squared plus y squared as long as we start from the origin, correct? This is held throughout for 3D space as well. For 3D, I have x, y, and z. I have x, y, and z. Z would be the height, right? So as an example, maybe I choose event first one to be occurring at 0, 0, 0, right? And let's say I choose this point. So maybe it's a bit hard to see because the graph is small. So let's just pretend this is 2, 1, 2, 3, 4, and let's pretend that to be 5, right? So 2, 4, and 5. So if I draw the line between the first event and the second event, the interval, let me call that h squared, is again going to be x squared plus y squared plus z squared. So in this case, it's going to be 2 squared plus 4 squared plus 5 squared. It follows the exact same method. So all we're doing is just x squared, y squared, z squared to find the distance between the two events, basically the interval between two events. Okay, we're going to do the same thing for space-time intervals as well. Now you might be saying space-time, okay, we're adding a time aspect to this because all we've considered right now was space, right? Space in the x-axis, space in the y-axis, space in the z-axis. If we're adding a time component to this or another axis to it, it becomes a 4D property, and it is a 4D property in real life. And you might be mind blown that there can be something called a 4D property, but we're not going to be considering 4D in physics because it's very hard to visualize. We're also rarely considered in 3D as well. We've always considered things in 2D. Let's say like projectile motion, we had vertical and horizontal, right? So we've always considered in 2D, so we're also going to continue concerning only 2D aspect. So now the space is going to be just x, the time is just going to be the y component per se, okay? So here I'm going to introduce you to space-time diagram, okay? So space-time diagram, you're going to have an axis called c times t. So we actually don't do just time, we do speed of light times time. This way it actually becomes a unit of meters, okay? And this is so that the intervals can be in 1 unit meters. And then here we have the x-axis, right? And this is also, of course, in meters, right? So as an example, how do we consider space-time interval or space-time events to be happening? So let's say, I have a rocket starting from 0, 0, and it travels to position, so this is 0, 0. It travels to position 5 meters in the x direction in, t equals 5 seconds, or it's going to be c times 5 seconds, right? So I'm just going to pretend that ct is equal to 15 meters. This is ct, and this is x. Okay, then it's going to be 1, 2, 3, 4, 5, and then somewhere like here. And we can actually, we don't even need to go straight like that. We don't even need to go straight to the endpoint. We can also plot along the way, right? And so that's going to be like plotting along the way, recording where it passes. For simplicity, we assume constant velocity, right? We don't vary the velocity. If it varies the velocity, then it can go up and down until there, right? But we consider it to be straightforward, straight constant velocity rocket. Okay, we actually call this world line, by the way, which is a line that's connecting these consecutive events. And events, by the way, you can think of it as positions as well, whatever you want, okay? Now, here's the thing. So how would I quantify this interval? We actually call that delta S. Well, Pythagorean theorem would say you do the ct squared plus x squared is equal to s squared, right? We actually don't do plus anymore, and it's actually minus, so this would be the equation. You don't actually need to know why. Some textbooks do plus, some textbooks do minus. It's just because we don't put direction in terms of time. For IB's sake, you're going to assume that this is negative. It's just I'm giving you a broad theory as to how we interpret this interval to be following similar to a Pythagorean theorem. Okay? And so we get this thing. Now, why is this important? Well, you're going to see in a bit. But first, the benefit of this space-time diagram, we call this space-time diagram, is we're going to be able to visualize simultaneity and time dilation or length contraction. And the way we do that a bit later is by adding reference frames. So this one is on one reference frame right now. We're going to be adding several and see how that's going to be the case. But don't worry if you're confused right now. It's going to be clear in about 2 to 3 slides. So first, let's do a practice problem calculating this. Okay, so pause the video and give this one a try. Okay, so we're given the velocity of the electron, and we're given the delta x. Okay, we can actually get delta t because v is equal to delta x over delta t. So delta t is going to be equal to delta x over v, which is, let me actually bring this here. So that's going to give me 8.43 times 10 to the power of negative 8 seconds. By the way, I'm assuming that's a typo in the question. I'm assuming that's plus because, well, speed of 5.93 times 10 to the power of negative 7 is very slow. We're not going to even be considering relativistic aspects of it. So assume that's to be true. And so we're going to get that delta t is equal to that. So now we can compute delta s squared. Delta s squared is going to be equal to c times delta t squared minus by delta x squared. And we get 614.8 meters squared, by the way. That's the unit. We're doing meters, so delta s squared is meters squared. Now, one thing I said about this time interval is that it's very, very useful to correlate between two different reference frames. And the reason why I say this is because I'm going to show it to you right now. The situation right now is we have a person and we have an electron traveling at 5.93 times 10 to the power of 7 meters per second. So this calculation of delta t and delta x and delta t are from the reference point A, right? What if I was on the electron, and that was the reference frame from the electron side. Well, we have to do Lorentz transformation, right? So let's try applying Lorentz transformation. So Lorentz transformation says, well, if I am traveling with the object in question, then delta x prime is 0. Because after, let's say, I get from here to here, I'm not changing the position relative to the electron. I'm always with the electron. So my displacement from the electron is 0, right? And delta t squared is going to be equal to this thing. So and I'm not going to solve this, but you can see how we can compute this from the reference of the electron. We've already done this through Lorentz transformation in the last video, right? Now, one thing that's special about this space-time interval is this thing has to also hold for the prime. Right? So we have this prime now, these values that we've calculated, right? If I plug it into here, I'm actually also going to get the same thing. Now, instead of doing Lorentz transform, because I know it's 0 and I know this is 614.8 meters squared, I can actually isolate delta t prime and calculate delta t prime as well. So I don't even need to know the Lorentz transform anymore. I don't even need to know the Lorentz factor. Right? I can just isolate delta t prime. Right? So this gives us another way to calculate delta t prime from another reference point as well. And so this is what makes it special because, okay, I can add a third reference point. Let's say I'm on a rocket. So let's call that reference point C, and I'm traveling at slower velocity. So let me do 2 times 10 to the power of 7 instead. Well, this is also another reference point, right? And I can also compute x prime and t prime, or in this case x prime prime and t prime prime, and that's also going to hold this equation true. So even if I have millions and millions of reference points, we can always agree on the space-time interval between two events. The two events being to travel from this point to this point. We can always agree on the space-time interval squared, or space-time interval as well. So that's really the crucial part about understanding space-time. Okay? Now let's go back to the diagram, and I can show you why it's important. This diagram is so important in relativity because you're going to be able to visualize time dilation and visualize length contraction as well. And so that's what we covered last video, right? So how do we do so? Well, first let me tell you about the significance of the slope. Every type of diagram we introduce in physics, there's either the slope or the area underneath the curve, or both that are important. So as an example, if I have v times t diagram, right, then the slope is actually the acceleration, and the area underneath is actually the displacement. We've already covered this in topic A1, 2, or 3, I forgot which one, but we've already done this way before. Same thing with force displacement graph. Force displacement graph, the area underneath the curve represents the work done to the system, right? So every diagram, it's either the slope or the area or both of them that's significant. For our space-time diagram, it's actually the slope. The slope, if you can see here, it's delta c times delta t over delta x, right? That's actually just going to give us c over v because guess what? This part is 1 over v. Okay, so it gives us speed of light over velocity of this object traveling. So in this case, it's the velocity of the rocket, right? So I can see from this diagram what the velocity of the rocket is. And that's dependent on the slope. Now, if that's the slope, then I can also find the angle here. Assume it's starting from 0, 0, by the way. The angle here is actually the flip of it. It's v over c. The tan theta is v over c. So tan inverse of v over c, it gives us the angle. So if I calculate the angle, I can also get the velocity as well. Okay? Now, by the way, for the exact same reason, when the angle is 45 degrees, this is when v is equal to c. So the velocity of the rocket is traveling at the speed of light. So here, traveling at the speed of light. Here, not traveling at all. V is equal to 0. So the lines are always going to be between here because you cannot exceed the speed of light. Okay, that's one thing. All right, so always remember that this line in the middle here is when velocity of the rocket or whatever that's traveling that you're trying to measure is equal to speed of light. Okay. Now, what if I add a reference frame? Because I've been looking at this rocket's trajectory from Earth, from rest, right? What if I get another rocket, a smaller one and a slower one, and I want to observe the rocket from this perspective, and I want to plot this time x prime and ct prime, because this guy is measuring x prime and t prime, right? It's no longer the same displacement and the same time. And of course, there's time dilation as well, right? So what if I want to add a reference frame? Well, I can do that, and it acts the same way. So this rocket will be traveling at certain velocity. And remember, velocity is correlated to the slope. So perhaps it's going to be somewhere like here. That's the velocity, and this angle will tell us the velocity of the rocket. Okay, and so this is actually the axis ct prime. And you might be thinking, okay, do I go down to make it perpendicular? Nope. We actually give the same angle on the x side as well. So this angle here is the same, and here it's going to be x prime. So let me just delete this to not make it confusing. So boom, we have added another reference frame. Okay, now why is this significant, you might ask? Why is this significant, you might ask? Well, because it allows us to visualize time dilation and length contraction. Let me show you. By the way, conventionally for this axis, all of the grid is straight like this, right? And the grid is like straight like this, right? The grid for these guys are like this. Okay, so it's warped. You're going to see in a second why, but it's warped. Okay, so it's not the conventional way, and we have to keep that in mind. So how do we visualize time dilation or length contraction? Well, here's why. So suppose, let's say I have 1, 2, 3, 4, 5, 6, and it's in a 1 second scale. So 1, 2, 3, 4, 5, 6. Basically, what I'm saying is the time between two events, these two, I see it as 1 second from the reference of the Earth, right? From the Earth's perspective. This is reference A, reference B, right? From my perspective on Earth, I see it as these two consecutive events happening within 1 second interval. Okay? But how about for these guys? Well, for the one on the rocket, remember that the grid goes like this, right? Okay, so the time between this guy and this guy, maybe it's 1.6 seconds on this axis. Okay, so that means we see a time dilation. From this guy's perspective, it looks like the events are happening between 1.6 seconds, but from Earth's perspective, it's happening at 1 second. So just by being able to incorporate this reference frame, we're able to see the effect of time dilation on a graph. Okay, it's the same thing on the other axis as well, where we can see length contraction on the graph as well. I'm not going to draw it out because you know, it's complicated. It's messy, but you can probably guess that the length between these two versus these two are not the same, right? So there's going to be the length contraction that we can visualize on this space-time diagram as well from different reference points. Now, I can also add millions and millions of reference points too, which leads me to something like this. So I can have reference point this guy, this guy, this guy. Maybe I have more rockets and more viewpoints of me observing the universe's events happening. Okay, and so I can always add these guys, and the line, this red line, is always when velocity is equal to c, which is the speed of light, and it's always going to be right down in the middle, because even after the graph has been warped, the angle from this side to here and this side to here has to be equal, because it uses the 45 degrees philosophy, right? And I also want to stress about the fact that we can agree on all of these frames, the space-time interval is the same. So let's say I have an event A at the origin, and I have reference point B here. Okay, the interval delta S is going to be the same. Delta S squared is going to be the same. So it's going to be C delta T squared minus delta X squared, which is equal to C delta T prime squared minus delta X prime squared, which is equal to C delta T prime squared minus delta X prime squared. So it's going to just continue with all the other reference frames as well. Okay, so that's the importance of space-time diagram. Just to recap, space-time, there's something called space-time intervals, so you can agree on the intervals between two events from any reference point perspective. We can also visualize that on a graph. We can also visualize time dilation and space contraction on this space-time diagram. Okay, so yeah, that's it on relativity. This topic is extremely difficult. So if you do have any questions, try to rewatch some of them, but you can always leave them down below in the comments and let me know, and I can try and get back to them. In the meantime, we'll be pushing out for more content, continue to push out more content on IAs as well, and what you should do over the summer as well. So stay tuned for more of those, and yeah, I'll see you in the next video. Hey guys, thanks for watching. If you like this kind of video, then consider giving us a like and subscribing to our channel. We have a lot more lecture style video and content like this in our channel, so feel free to go check it out. If you're looking for additional guidances like one-on-one tutors in IB subjects, SAT, TOK essay, IAs, writing, etc., then go to our website at NovaEdgeAcademics.com, fill out the form, and we'll get in touch with us. In the meantime, we'll see you in the next video.